So in this video we're going to be taking a look at a review for the exam 3. And just to give out a few notes about the exam before we get started, the exam will be over sections 3.10 first. That was the linear approximations and differentials. And then 4.1 through 4.4. Then we skipped over 4.5 and 4.6 and did 4.7. 4.9 and Appendix E. Good. Yeah, Appendix E is really getting things set up for the next chapter, Chapter 5. Okay, so the exam will be run pretty much the same way as before. We'll have 90 minutes total. And so Canvas will be doing the timing, right? Canvas will time it. It will be open notes, open book. So you could also look at your homework, of course. I would recommend having a calculator handy. Calculator, you don't really need a fancy one, just something that will do some basic arithmetic. And then you can also use the class website. Oops. And that's the only website, right, that you'll be allowed to use. Good. Now just to say a couple things about the Open Notes Open Book. I know it's easy to let the studying slide because you will have your book in front of you, but because this is timed, right, you're not going to have time to look everything up. So it is important to go through all of the review material that I posted on the internet, just so you're very familiar with it. And so, you know, as you're going through the homework problems or the review problems, you might make a note of the things that you're not sure about and where you can find the information that you need. You might also just make a note, make a set of notes of things that you're not sure about. That way you'll have those things right in front of you instead of having to look things up in the book. Because, yeah, the reason there is a time is because, without time you can basically start everything from scratch. And, yeah, you're not the exam's really not designed to be done in like a week. It's designed really to be done in about an hour. Okay? All right. And so, how is this exam going to be arranged, I guess, is the next question. What are the topics? So I've listed the book sections, but let's take a look at how you might think about this material being arranged. And so this section of the course is really about applications of the derivative. And so the main applications of the derivative are linearization and approximation. Whoops. Right, and we saw that in section 3.10. Where should I put the 3.10? 3.10. Okay, and so for the linearization, do you remember what that is? Linearization is the tangent line. So we use a tangent line approximation for f, and then the approximation part is using dy for delta y. Okay, and so we should remember the definition of both of those things, delta y and dy. Maybe I'll just write them off to the side here. So delta y is the actual change in y as f changes. So this is the actual change in f in your function, and then dy is the approximation. And using the differentials, right, we think of dy over dx as f prime of x. So then just multiply both sides by dx. Good, and so we're using the dy to approximate delta y. All right. Good. And so we'll do some more detailed examples of that in just a second. But I just wanted to kind of finish off um, our set of topics here. So another thing, a main thing that we talk about is the shape of f of x and the EVT, right? And so what I mean by the shape of f of x is we go through and talk about f is increasing, decreasing, f is concave up, concave down, right? And so that's going to entail finding the sign, SIGN, of f prime and f double prime, right? And so we might have to do some sign chart stuff here, right? Okay, and so that's what we mean by the shape of f of x. Oops. We also defined local extrema and global extrema. And that's where the EVT comes in, right? So the EVT says that we have a global maximum if we have a continuous function on a closed interval. Good. And so that kind of led us down to optimization. And if you go outside of calculus and somebody says, or if you're thinking about what things apply from calculus to like the outside world, it's really this section, optimization, trying to find a maximum or minimum of some function. So for example, if you can define an error function in your algorithm, then you would try to find a set of parameters that try to minimize that function. Okay, and so the optimization part of calculus is really where most of this stuff is applied. Good, and we've actually seen some of that, right? When we're trying to figure out where to land a boat, right, to maximize or minimize our time of travel. And there's some interesting tie-ins to psychology. Oh, maybe I'm going off on a tangent. So one question might be, do animals or people actually optimize their time? You know, if this was a physical situation and you needed to get from point A to point B, although you're not saying, okay, I'm getting off on a tangent, but it is kind of fun to think about whether or not people actually find a point that optimizes their energy, right? Minimizes or maximizes their energy. Okay, so now let's continue around the bend here. How about the mean value theorem? This is a big one because it's also Rolle's theorem, right? And so the Rolle's theorem is a special case of the mean value theorem, really, although we use Rolle's theorem to prove the mean value theorem. Once you've got the mean value theorem, Rolle's theorem is a special case. Okay, and so just as a reminder what that is, right, if I have a function for the mean value theorem, and it goes from here to here, from a f of a to b f of b, and it doesn't matter how the function works there, if I look at the slope of that line, that's got to be equal to the slope of the tangent line at least one place. Good, so that's the mean value theorem. And another way to think about the mean value theorem is that the average velocity must be equal to the instantaneous velocity at some point in time, right? From A to B. Good. Let's see, some other things we talked about were L'Hôpital's rule. So it's typically spelled L'Hospital, although you can spell it without the S if you like. If you put a little hat on the H, maybe I'll write it down here. If you do that, that's an alternative. Of course, if you look it up on the internet, there's going to be 10 other ways of writing it, but these are well, this first way is actually the way that L'Hôpital himself wrote it, so maybe we'll just erase this other one. We'll be bucking the trend. Good, and then for L'Hôpital there was a basic rule that involved a fraction, right? But then there were some algebraic conversions, right? Algebraic conversions for other indeterminate forms. And what were the other indeterminate forms? Well, if you have something like 0 times infinity, that's an indeterminate form because we don't know if a limit would exist for that or not. It's possible that it does. Okay, another one would be 0 to the infinity power. That's another one that is hard to, well, you can't figure it out in advance. Okay, looks like we're getting short of time, so let me go ahead and finish things up here. We have the antiderivatives as kind of a separate application of the derivative. And this is this together with our last section, oops, Appendix E, which are the sums. That's going to prepare us for Chapter 5. Prep for Chapter 5. Okay, but of course they will be on the exam. That's just why we're setting things up for Chapter 5 right now. Good, and so that's the layout. Again, we have our linearization and tangent line approximations, shapes and the extreme value theorem, increasing, decreasing, concave up, concave down, optimization, antiderivatives, L'Hopital, mean value theorem, and Appendix E. Good. So that's what's going to be on the exam. In the next video, we'll just try working through a few random problems. See you then.